Hello everyone. So this is the lecture for 421. So we have two lectures remaining and I would like to spend those lectures reviewing the content of the course. So first off, we have our final Thursday the 30th at 9 a.m. I plan to have it similar to the previous exam. Aside from the fact that you will be given 2.5 hours because it is a final. So let's remember the final exam is worth 40% of your grade. Not only that, I said that if you did better on the final exam, it would be able to also replace your lowest midterm exam grade. So technically, you can, if you do really well on it, you can think about it as worth 55% of your grade. So with that in mind, I would suggest that you spend an adequate amount of time going over the material. Okay, so again, it's on your syllabus, but uh, Thursday the 30th at 9 a.m. Okay, so um, I want to spend some time going over some practice exams. So again, the final is cumulative, so you do have to remember everything that we discussed in the course. I think for the material for the first test, um, at least in the probability section, a lot of the questions should remain pretty unchanged by the new format of the course. Okay, a lot of the probability questions you should still just have to calculate kind of by hand or whatever like you normally would, and then simply select the multiple choice answer that is most appropriate. So let's go ahead and look at this is the final exam solutions number one. Okay, so um, here we've got a contingency table, and I'll just for time I'll skip the variable specifics. You can kind of read the problem. But we've got two variables. Okay, we've got D and C. Okay, or two events. And well, we can see we want to use the table to determine if C and D are independent. Okay, and of course, this is D complement and this is C complement, right? Remembering way back, right, which is basically the opposite. Okay, C not C, D not D. And so we're trying to determine if C and D are independent. Okay, and we have to use probability to justify our answer. Okay, so recalling there are three definitions of independence. Okay, um, one thing, of course, I would recommend you having your notes up during the exam. Um, However, a lot of this stuff, hopefully you remember, because if you're having to look every single thing up for every single question, you're probably going to run out of time. Okay, so recall there are three different definitions of independence. You could choose any one of the three definitions, but you can see here, I'm trying to verify that the probability of the intersection of C and D is equal to the probability of C times the probability of D. Okay, recall that's one of the three definitions of independence. If you don't remember the other two, I recommend you looking back through your notes or the course notes to verify them. Okay, because depending on the problem, you may need a different one. In this case, you could have used any of the three though. Okay, so the probability of C and D. Calculating that in a contingency table would simply be looking for the intersection cell. So we're looking for the column with C and the row with D. So that would just simply be 1. And then we have to figure out how many observations we have. So just adding everything up, and that's 60. And so the probability of C and D is 1 out of 60. Similarly, the probability of C would just be adding up everything in this column, so 20, and then of course there's still 60. Probability of D is 3, and again out of 60. So multiplying those together, they are the same. Okay, so the intersection is equal to the product of the two individual probabilities, thus they are independent. Okay, and so what that means in this case is that, well, the variables that the thermal coating does not affect whether the ship takes damage upon reentry because the two variables are independent. That's kind of putting independence in context of what it actually kind of means in this problem. Okay, we've got 100 batteries, 5 are defective, but we don't know which 5 are defective. Okay, the machine requires 5 working batteries to operate, and so if we randomly take 5 of the 100 batteries and put in the machine, what's the probability that the machine is not operational? Okay, so again, classic probability question, and I think a lot of these questions, right, you of course you have access to everything, you're at home, but a lot of these questions say Googling is probably going to be very little use, I would imagine, okay, because there's just so many different things going on in the problem that you really have to have an understanding of how to go about the problem. Looking things up is probably not going to be helpful for some of these questions like this one. Okay, so we need to recall back, right, where we're dealing with probability. And so one of the most common things is, do we have a named distribution that might measure the quantity that we're interested in? Okay, and so this is a kind of a multi-layered problem, and we really have to be careful about trying to understand the problem, where it's very easy to make a mistake or just not have any clue how to do it whatsoever. Okay, so first off, right, we've got a set number of batteries, 100, and we know the exact number that are, say, type 1, okay, and thus, of course, we also know the number that are type 2. And so in order for this machine to work, we have to have 5 batteries, basically, of type 2, right? And so we're going to take 5 batteries out, and we want to know the probability that the machine is not operational. Okay, so there's lots of ways for the machine to be not operational, right? If at least one of the batteries is defective, then the machine will not be operational. So thus we would have to calculate many different probabilities. However, if we remember the complement rule, there's only one way for the machine to be operational. That is that we get 5 non-defective batteries, right? There's only one way that we can choose 5 batteries and have all of them be non-defective, right? Each one has to be non-defective. Okay, so that can only happen one way, and thus that should be an easy probability to calculate. And so from the complement rule, we can calculate that probability and subtract it from 1. Okay, so here I'm letting O denote that the machine is operational, and X be the number of non-defective batteries chosen, okay, when we choose 5 batteries. Okay, so the number of non-defective batteries that we choose has a hypergeometric. Okay, the reason that it is not binomial is because we have a set number of objects and we know the proportion that are type 1. Okay, if it was going to be binomial, remember, there would have to be independent trials such that one trial did not affect the next trial. But once you start picking batteries out, whether the first battery was defective or not affects the probability that the second battery that you pick out is defective or not, and so on. Okay? So, but of course, for either binomial or hypergeometric, we have 2 outcomes, which is we are getting a defective or non-defective battery. Okay, so by the complement rule, right, the probability that we're looking for, which is that the machine is not operational, right, not operational, is 1 minus the probability that the machine is operational, okay? And there's only one way that the machine is operational, and then that is out of the 5 batteries that we're picking, we get X to be equal to 5, where, right, we get 5 non-defective batteries. And so hypergeometric, one of the things that I also think you should have pulled up, I'll send this to you along with all these exams just in case you've lost it. Hypergeometric, here's the mass function. Recall, right, for discrete distributions here we have mass functions, and for continuous we have density functions. But nonetheless, remember y's are just like x's, or they're just your variable, what's denoting your variable, which is arbitrary, so these are y's. But nonetheless, here's our hypergeometric. Oh, this is kind of an ugly one, right? But as I said before, I would spend more time understanding what these things are rather than trying to remember the letters themselves. Okay, I think if it's more intuitive and logical to actually just remember what this is trying to represent. Okay, one of the few. But it is that out of the 95 batteries that are not defective, so type 1, okay, and again you could choose defective to be type 1 and you'll still get the same answer. You just have to keep track of what's type 1 and what's type 2, okay? So out of the 95 batteries that are not defective, I want 5 of them to be not defective. So 95, choose 5. Out of the 5 that are defective, of course, I need 0. I don't want any defectives out of the 5. Divide those two by, out of the 100 batteries, of course, I'm choosing 5. Okay, so out of 100 batteries, I choose 5 in the denominator, and in the numerator, out of type 1, I want 5 type 1s, and out of type 2, I want 0 type 2s. Again, non-defective, defective. And of course, these are the choose, right? These are the binomial coefficients. So, of course, you also most certainly need to remember what this is. And right, anytime we have an n choose x, I'll go back to the generic. Right, anytime we have like an n choose x or whatever choose whatever, it's just, in this case, n factorial divided by y factorial times n minus y factorial. Okay, so, but right, in general, right, when we have it's n factorial, I can't really do a good divided by x factorial times n minus x factorial, right? Okay, and that's what n choose x is, right? N factorial divided by x factorial times n minus x factorial. Okay, so for example, 95 choose 5 is 95 factorial divided by 5 factorial, and then also, right, in the denominator also is 95 minus 5 factorial, which is 90 factorial. Okay, so just the first one, let's recall. So that first one is going to be 95 factorial divided by 5 factorial times 95 minus 5 factorial, and simplifying one more time. Right, this is just 95 minus 5 factorial is just 90 factorial. So it's 95 factorial divided by this, and this is, right, 95 times 94 times 93, right, etc. For each one, you just multiply them. But if you don't know how to put this in a calculator, I certainly don't. There should be a built-in function in R too, but honestly, I'd have to look it up. It shouldn't be too hard to look up, though, if you want to look it up. But really, if we understand what these are, this is just nothing more than just, I'm going to rewrite 95 factorial, okay, as 95 times 94 times 93 times 92 times 91 times 90 times 89, right? Times 88 times 87 all the way to 1, which is 90 factorial, okay? And so we've got a 90 factorial in the denominator and numerator, so we can kill it. And so now we've got, and of course simplifying 5 factorial times 2 times 1. So now we just have to plug this in, right? 95 times 94 times 93 times 92 times 91, and divided by 5 times 4 times 3 times 2 times 1. Of course, making sure you put parentheses and so that you're dividing by all of this. And so it's relatively easy to put that in a calculator, even if you don't know the factorial function. Okay, and so that's how we get the first. And likewise for the second and third. Now, technically, you could use another thing, right? We already just said this is a hypergeometric distribution, so you could use the D hyper, right? D calculates individual probabilities, okay? Now, the one thing is, right, there's lots of different arguments, so question mark D hyper, if you want, you can just basically just type it in R, okay? However, you need to make sure you put each argument in the right place and you understand what each argument is, okay? So if you want, that's also an alternate way to do it. And you just have to look up the arguments and make sure you put them in the right place, okay? Either way should lead to the same answer, okay? So I might suggest verifying that you can in fact get the correct answer on this question. Just not that the math is crazy hard or anything, but it's easy to make mistakes, and just for a little bit of practice, I might suggest verifying either that this is 0.23 or figuring out how you can do it with that D hyper operator in R, okay? Right, for these exams, pretty much any way you can go about getting the right answer is sufficient, okay? So either way, I would make sure that you can solve this problem. Okay, let X be the number of rolls of a die until you observe the third 4. Okay, what name distribution does X follow? Okay, it follows a negative binomial distribution. Okay, but for yourself, thinking about why this follows a negative binomial distribution, negative binomial counts the number of trials until the rth success. Okay, the number of trials until the rth success. Okay, so we have to realize that R, well, first off, it's a negative binomial distribution because of that, but of course it's going to be asking us something, in this case the expected value. Okay, so we need to know what R is, which is 3. And of course we also need to know what P is, which is the probability of getting a success. And okay, a success is getting a rolling a 4. Okay, so the probability of success is obviously just 1 out of 3, 1 out of 6. 6 faces on the die. Okay, so what is the expected value? This is the one where you need to either remember it or it shouldn't be too hard to look it up. And it's just going to be R over P, okay, which is going to be 3 over the 1/6, which is 18. So we expect to roll the dice 18 times before we observe a third 4. Now, one thing I will mention for some of these expected values and variances, if you do not remember them, I would highly recommend that you look them up in your notes versus online. I believe we talked about it. Yes, we did talk about it because in R, whenever we try to calculate negative binomial and geometric probabilities in R, we had to do a little special trick, okay, where we modified the number of trials to the number of failures. I don't know if you remember that. We had to do a slight modification in R whenever we typed in something like dgeom or d in binom. Okay, because these functions are now calculating the number of trials, but they're calculating the number of failures. Okay, so if you were to say just look up on the web the expected value for a negative binomial distribution, it's possible that it could give you R over P, okay, um, but it could give you the expected value formula for a negative binomial distribution counting the number of failures, okay, which would be RQ over P, I believe, okay, which of course would be the wrong answer in this case. So I just want to warn you about that. If you look some of these formulas up, um, especially for the discrete distributions, some of these, it could give you the wrong thing. Okay, anyway, the variance, okay, RQ over P squared, we can remember that or look it up, and we just have to plug stuff in, okay? As long as we understand what the things are, that should be pretty easy, okay? So, but again, for this problem like this, right, it probably take us, 30 seconds to complete all of this if we memorize this. If not, it could take us quite a few minutes to look everything up. Okay, so just mentioning that to bear in mind because you have to memorize, you have to understand some of the course material. You can't just rely on looking it all up, or you're certainly not going to have enough time. Okay. The lifetime of a machine looks like this. Okay, so first off, it says PDF, but we should be able to realize that it is not a PMF because the support is continuous. Okay, it doesn't say it's a named distribution, but if I look at it, it looks pretty similar to a named distribution. So looks a lot like this. Okay, so this is actually a gamma distribution, but it doesn't say it's a gamma distribution. Okay, but anyway, calculate the CDF of the gamma distribution. Okay, this is one where you may actually have to do your integrals. Okay, there is not a closed form for the CDF of a gamma distribution in general. Okay, so but with specific values of alpha and lambda, we can derive the CDF. So back a long time ago, in order to integrate the gamma distribution, we had to use integration by parts. That was the go-to trick to integrate a gamma distribution. Okay, so trying to integrate this, right? Notice I just switched to y's. That way the CDF could be in terms of x. Okay, but anyway, setting u equal to everything else basically, and setting dv to contain the e, right? Then we have u, a derivative of u. Okay, remember gamma of 2, that's a constant of some sort, which we need to figure out at some point, but for now we can just chuck it in here and just pretend it's a constant. And so dv, integrating, right, very, very simple integration on this. And so we get uv, evaluated at our bounds, minus the integral of v du. Okay, uv minus the integral of v du. Okay, and integrating this is very simple, very simple. And so we get this, and just evaluating it x and 0, just hopefully it's solid, but recalling whenever we evaluate an integral, right, we stick in the upper bound, and then we subtract from that, we stick in the lower bound, right, but we have to make sure we subtract. Okay, whenever we stick in the lower bound, you have to subtract. Okay, so if we do all that properly, we should get this, and again, I would recommend doing this integral yourself. just to make sure that you are not rusty on something that you didn't realize you were rusty on. Okay, you should be able to get to this. And then now recalling what the gamma function evaluated at 2 is. Gamma of 2 is 1 factorial, which is just 1, right? Recall 0 factorial is also 1, just a reminder. Okay, but in general, gamma of, say, 5 is 4 factorial, right? Gamma of 11 is 10 factorial, right? It's just subtract 1 from the number and then take its factorial. However, we can't do that for non-integers, right? But there's only one special non-integer that I expect you to remember, which is gamma of 1/2, which is the square root of pi, which I guess you could just probably try to look up. But also, if you had something like gamma of 3/2, we would need to use the iterative or recursive relationship of the gamma function in order to solve like gamma of 3/2. Okay, or you could probably look that up. Anyway, this is what we get for the CDF. So I think you should, this is one of the few problems that you may actually, it may actually be easier for you to just understand how to do it than try to look it up. Okay, so I think integration by parts is something, I mean, personally as an engineer, that you should be comfortable with. It's a pretty basic technique. Okay, so try to make sure that you can get the CDF. Okay, hazard function. Hazard function, we know its definition, PDF divided by survival function. Recalling survival function is nothing more than 1 minus the CDF. So it gives you greater than probabilities, right, whenever you stick a number in. And just like the CDF, right, we can actually stick a number in to get a probability. We can't in a PDF, right? Recall you can in a PMF for a discrete distribution, but for a continuous distribution, you can't evaluate little f at single probability points, right? So we know the PDF, and we just calculated the CDF, so we can 1 minus the CDF, and we get this. So this is the hazard function. So notice this is, I'm now asking whether the machine is getting stronger or weaker. And this is not a Weibull distribution, right? So you can't use that, what was it, the alpha greater than 1 trick, I think it was. Okay, so this is not a Weibull distribution, so there is no trick, at least that we talked about, in terms of determining whether the hazard function is increasing or decreasing. So we need to take its derivative, right, to determine whether it is increasing or decreasing or neither. Okay, so taking the derivative, in this case, right, we actually have two functions of x, so this is actually one of the more annoying ones, right? So, man, it's been a while, right? Take the derivative of the top, right? So this is the division derivative rule, right? And so it should look like this, okay? And it's strictly increasing. It's positive, okay? Notice x is positive, right? So it doesn't matter whenever we plug an x in, it's always going to be positive, and thus the hazard function is increasing and the machine is getting weaker with time. Okay? All right. What's the probability the machine lasts at least 3 years given that it's still functional after 2 years? Okay, by now, hopefully, you can easily understand that this is a conditional probability. It's asking the probability that x is greater than 3, given that x is greater than 2. And basic probability rules give us the second statement. And we understand by now we're talking about time, and thus the numerator can be simplified. X being greater than 3 implies that it's greater than 2. So we have x greater than 3 divided by probability x is greater than 2, which is nothing more than survival function evaluated at 3 divided by survival function evaluated at 2. And we know what that is, right? 1 minus the CDF. So just simply plugging it in and we get our answer. All right. Okay, we've collected data. We've got some stuff below. Okay, so this is kind of, I think every question to this point is relatively the same as far as how you do it now as to how you would do it before this incident. We've gotten to the confidence intervals, and recall for the most part I expect or think you should just be doing these confidence intervals in R now. Okay, and so I'm not going to give you a question where I give you a bunch of these numbers, right? What I'm going to give you is a data set, okay, and expect you to be able to analyze the data in R and to come up with the confidence interval. Okay, so, but let's look at it. We want a 90% confidence interval for the true average turbine speed. Okay, another thing that you could have out with you, maybe it be helpful for you, I'll send it to you again, the sheets for Formula 2, or for the Exam 2 formulas. Okay, now for the most part, these certainly aren't as useful as they would have been to you before. Okay, but certainly we should understand what we're doing a confidence interval for, which is the mean, one sample mean. Okay, but we don't really need to know this formula exactly anymore. Okay, what we need to do is use it in R. So understanding that we're looking for a confidence interval for the mean. Okay, let's see. 30 turbines. This is what I'm going to do. I'm just going to fake a data set real quick. Now normally I would give you a data set and you'd have to read it in, and I'm sure we'll see practice either today or next lecture about reading it in again, although we've seen quite a few. But basically, you're going to have some data set, okay? Okay, well here. Okay, it says the means around this, so I faked the data a little closer to this. Okay, so a 90% confidence interval for the true average turbine speed. Okay, let's assume data, this is the 30 observations that we read in on our data set. Okay, and if you want to fake your own observations, just type in this line right here. Okay, data is equal to R norm, parentheses 30, 300, 25. Okay, that should give you similar, not exact, similar observations. Okay, and so if we want a confidence interval for the mean, recall t.test. I sent this to you, so if you have it, great. You should have something that I sent to you. Might be helpful for you, but we can see for one sample mean, right, t.test, we put our data set, comp.level, if we want something different than 95, which we actually do in this case, okay? So t.test, put my data set, which is simply called data. Remember, this is whatever you call your data set. If you actually have a special name for your data set, you just have to put it there. Comp.level is equal, we wanted a 90% confidence interval. Okay, one sample t-test, 90% confidence interval, bam, okay? We're 90% confident that the mean, I think we were talking about turbine speed, is between 298 and 314 miles per hour, whatever units it was. Okay? Revolutions per minute. Okay? And so, right, we don't need these anymore. We need to know how to do it in R. Okay, right? We get similar numbers, but so our case is 298 to 314. What are the assumptions of the confidence interval? Right? We assume that we have a random sample and the population is normally distributed. Okay, okay, it didn't ask us to answer a question. Okay, normally I ask you to answer questions. Okay, so the most common question, right, for a problem like this is I might say something like, if the average turbine speed is below 300, then, right, it needs to be tuned. Okay, we want the turbine speed to be at least 300 RPMs. Okay, and if it's not, we need to retune it. Do we need to retune the fan or whatever turbine? Based on the confidence interval, right, what's our decision? 300, the number that we're looking for, is between the upper and lower bound. Thus, we do not have evidence that the turbine speed needs to be, or that the turbine needs to be tuned, okay? Because we do not have evidence that the turbine speed is less than 300. However, we also don't have evidence that the turbine does not need to be tuned, right? We also do not have evidence that the turbine speed is above 300, right? So this is the case, right, when the quantity that you're looking for is between the upper and lower bound. That's when we basically don't have evidence of any position. Okay, we don't really have a conclusive decision to say. So it's we can't say that it does, we can't say that it doesn't. Okay, remember that. All right, 98% confidence interval for the ratio of the variances. I'm pretty sure, let me try to remember here. We definitely did all three regular cases, or one sample cases, mean, variance, proportion. We did two population proportion. We skipped these, right? We skipped the ratio of two variances, so two population variance. We also skipped two population proportion. Okay, so, oops. This question would not be on the final. Okay, this is one of the things we had to skip. Okay, if you want to look at it for your own self, you can, but that's not going to be on the test or on the final.